All right, good afternoon, everybody, and welcome. Welcome to the Applied Physics Lab, however virtually it is. We are excited to have you here today, and congratulations on making it through this many rounds of competition. Today, we're going to share with you some of our spacecraft progress on the DART mission. DART is a robotic spacecraft, and our theme today for our presentations is extreme space: design, build, test, and operate. And now I'm going to hand the program over to Amber Dreisman. She is the MTI representative. Amber?
Hi, welcome to the Maryland Tech Invitational STEM Exposition that is brought to you by the Civil Space Mission Area of the Johns Hopkins Applied Physics Laboratory. APL has graciously hosted this enrichment program since the inaugural MTI 4 years ago. And we are grateful to the lab for continuing to inspire the young engineers who compete at the MTI. As a thank you, we actually have some commemorative 4-year coins that we are going to be giving to key individuals who, without their excellence, this tournament would not exist. The first one will go to Dr. Ralph Semmel, who is the director of the APL. Dr. Semmel spoke at the first MTI, and he was the inspiration for the MTI intern networking program. He was so impressed with our students that he handed out his business card, asking them to contact him about intern opportunities with the lab. His wholehearted belief in our students emboldened us to create the MTI intern networking program. We also are sending coins to Dr. Michael Ruskevich. He is the head of the APL's Space Mission Area and who has been a fervent supporter from the beginning and has facilitated APL's involvement. We'd also like to give a coin to Dr. Jason Callery, the Mission Area Executive of Civil Space. Dr. Callery continues to be an enthusiastic lead and is here with us today to share an overview of some of the cutting-edge space missions currently underway at APL. And we'd also like to give one to Carrie Beiser, who has done a fantastic work organizing this program year after year. Thank you all. And now I'm going to turn it over to Dr. Callery.
Hi, can you see the slides okay? Hi, just checking if you can hear me.
Yes.
Can you see the slides as well?
Yes, we see you in slide view mode, not show mode.
Sorry, give me 1 second. Is that better?
Yes, thank you.
Okay, sorry about that. Well, good afternoon, everybody. Thank you so much for attending today's event, and as Margaret said, congratulations for how far you've made it in this competition. So my name is Jason Callery. I am the Mission Area Executive for Civil Space here at APL. It's a real pleasure for me to be able to share a little bit about what we do here at the Johns Hopkins University Applied Physics Lab with you. Just a little bit of background. So I am an astrophysicist by training. I grew up in Canada. I studied physics and astronomy at the University of British Columbia in Vancouver. I've been excited about space since as far back as I can remember. And when I was your age, I realized that there was a way for me to really make an impact on our understanding of space. And I never looked back when I had that opportunity. And so it's been an awesome ride. I spent some time, 4 years, in fact, at the University of California in Santa Cruz as a postdoctoral researcher. That was a great opportunity for me to branch out and expand my research program and also network with a lot of colleagues and build partnerships with the community. And then I moved to Maryland about 12 years ago. And there I continued to develop my research program, but I also fell in love with understanding how NASA builds space science missions and operates them, and grew into various leadership roles in helping motivate and manage those kinds of opportunities. So It's been a wonderful experience for me, and I really enjoy sharing what we do in NASA Space Science program with students and with the public. So it's a great pleasure for me to be here today. Before I talk about our program at the Johns Hopkins University Applied Physics Lab, I want to talk a little bit about our history. And so let me start with this picture. This is a picture of a V-2 rocket. This was a weapon of destruction in World War II. The Germans built more than 3,000 of these rockets. And these were being built and launched and tested around the same time that APL as a lab, and in fact, a lot of the R&D labs in the US were set up and were getting underway. Shortly after the war, the US got their hands on about 60 of these V-2 rockets, and they began testing them, asking questions such as how can we use these rockets to explore space? And one of the founding members of APL, a scientist named Dr. James Van Allen, was asked to serve on an advisory committee from where these rockets were being launched. And one of the first experiments he and his colleagues did was they put a camera, a 16mm film camera, and pointed it out the window of one of these rockets as they launched it. This rocket traveled above the von Karman line, it exceeded space, and it caught this beautiful vantage of our planet Earth. And so this is in fact the first image of a planet that's ever been taken from space. It's the first picture of Earth taken from space, and that was taken by the Applied Physics Lab. So space exploration is really a part of the DNA of APL since its first couple of years since the lab was set up. The lab also played a major role in responding to events that happened shortly after that. So this is, of course, a picture of Sputnik. And so the Russians launched Sputnik in the late 1950s, and it was a rude awakening for the country. There was a lot of angst and uncertainty as to what the Russians were doing in space. And as we set a goal of understanding that, some of the lab's scientists and engineers were among the first people to figure out exactly what Sputnik was doing. And so one of the first things they did is they began trying to listen to Sputnik so they can understand where the spacecraft was at different times. And it's a wonderful story because one of the first conclusions that they made is that something must be broken in Sputnik, because the way that they were hearing it, there's an oscillation that kept moving around. And so they initially felt that way, and then they quickly realized that no, it wasn't that anything was broken, but we were actually hearing the Doppler shift of the spacecraft. We were able to listen to the Doppler shift of the spacecraft and see it as it's coming directly overhead and as it's receding away from us. And so this was a big discovery. It allowed us to understand the orbit of Sputnik, but then the scientists and engineers took it a step further and said, well, if we know exactly where the spacecraft is, we can use the spacecraft to pinpoint where we are. So they turned that problem around and they began developing what became the first experimental satellite navigation system. And this was done, within a year or so of the finding. And they actually built a constellation of these satellite systems. It was called the transit satellites. And they launched these, and this was very beneficial to the US because it allowed us to pinpoint the locations of our submarines and our naval fleet at the time. And this eventually became the precursor of the modern day GPS system that everybody is very familiar with. And so these kinds of defining innovations have been a part of APL again since the founding days of the lab. A few years after that, APL actually captured the first full disk color image of Earth from space as well. This was a part of an experiment to study the gravitational effects on Earth when you launch a spacecraft. So stepping forward, the civil space program that Amber alluded to is the part of APL where we work very closely with NASA. So NASA is our sponsor, and we partner with NASA to enable incredible scientific discovery and space exploration and new technologies and new engineering that can change the way that we look at space and understand what our place within space is. NASA, of course, is one of the biggest brands in the world. And has made some of the most foundational and inspirational discoveries across so many different themes. Within NASA as an agency, about a third of the work that NASA does is something that falls in something called the Science Mission Directorate. And so that's a part of NASA that's motivated by answering science questions and expanding our scientific understanding of the universe. And there are 4 divisions within NASA's Science Mission Directorate: Earth Science, the study of Earth; astrophysics, which is a study of everything beyond our solar system, essentially; planetary science, which is a study of all planets and asteroids and comets and moons within our solar system, except for Earth; and heliophysics, which is a study of not only the sun, but also how the sun impacts our solar system. And so in our civil space program at APL, we have core expertise that's aligned with the kind of engineering solutions and scientific questions that arise in each of these domains. So we can play a leading role in providing answers to those questions. Framework that we have here at APL is to really have the capabilities on site at the lab to be able to develop space missions with an end-to-end framework, from the cradle to the grave, everything that you need. And for us, that starts with scientific research. We have active scientific researchers, more than 100 of them, in fact, in the space exploration sector. They're experts in all of those core topics that I just mentioned. They write research papers. They write hundreds of research papers each year. They sit on NASA committees to advise NASA. They sit on National Academy committees. And so they're a part of the workforce in the country, the technical workforce in the country that's helping identify new scientific challenges to go after. But then we also have all of the abilities within our engineering teams and within our technical teams to conceive, design, build, test, and operate those missions and those solutions that we put forward to answer those science questions. And of course, when those missions are operational, they reveal new puzzles. One of the biggest rewards from launching a new mission is not answering the questions that motivated it, but it's turning up all of the new mysteries that you have to go forward with on your next experiments. And so this is a wonderful framework that we have at the lab. We're one of 3 organizations in the US that has this full end-to-end space mission development capability for large NASA missions. When you're talking about programs that are, say, $500 million and higher, there are only 3 organizations that can do that, and APL is one of them. This model has served us really well. This is a fleet chart showing all of APL's future, current, and past space science missions. And so everything that you see on here was developed by APL. There's no other organization in the world that can show you a chart like this when it comes to planetary science and heliophysics, the 2 core areas of our expertise. And there's a lot of incredible firsts when you look at this chart. So if you look at the NEAR mission, for example, there on the right, that's the first mission to ever rendezvous with an asteroid, orbit around that asteroid, and eventually land on that asteroid. It's really a trailblazer for so many missions that NASA has built since then to study asteroids. You look at the New Horizons mission to the right of NEAR, that's the first mission to explore the outer solar system, including Pluto, the dwarf planet in the outskirts of the solar system. You look at Messenger on the left, that's the first mission to successfully orbit Mercury and the first mission to study Mercury in detail, and lots of other great examples across this fleet chart. We also develop a lot of science instruments in the civil space program at APL. These are instruments that not only fly on the missions that we develop at APL, but we often partner with other organizations. We partner with other agencies, in fact. So if you look at, for example, if you look at Mars on this chart, you can see something called Magani right next to Mars. Magani is an instrument that's going to fly on a mission that's being developed by the Japan Aerospace Exploration Agency to do a sample return from one of the Martian moons. We're actually going to pick up rocks from one of the Mars moons and bring it back to Earth. It's very inspirational. And Magani is the key instrument that's going to do all of the compositional study and help identify the site location for where to get those rocks from. And lots of other great science instruments across that have flown across the solar system that have been developed by APL. And in fact, this picture only shows you the future and current instruments. If I showed you all of the past instruments over our history, this would be a very busy map. So let me walk you through a couple of our incredible success stories. And I want to start with New Horizons. This is our tried and true spacecraft that flew to the outskirts of the solar system. We launched New Horizons in 2006. It had an awesome journey. It basically hibernated for 9 years. And then in 2015, it came up to Pluto, had to turn on and work as intended. And it was the first mission to open our eyes to the beauty and the wonder of Pluto, made countless scientific discoveries on the geology and the formation of Pluto, and lots of science facts that I'm sure you've already read about and you've already learned about. One of the things with New Horizons is, it was a flyby mission. So New Horizons didn't enter orbit around Pluto. It just shot past Pluto, moving 30,000 miles an hour. And so as it moved past Pluto, it's just headed into the outer solar system. And so our scientists here at APL, working with the science community, came up with a very clever experiment to try and find something that happened to lie along the trajectory that New Horizons was flying in the outskirts of the solar system, and study it in more detail. And so we used a number of ground-based telescopes. It was very difficult, very challenging observation. We weren't able to find something. And then eventually we got a large allocation of time on the Hubble Space Telescope, the mighty Hubble Space Telescope, the biggest space telescope that we have. And we pointed Hubble and we were able to find something that looked to be at the right distance and along the trajectory of New Horizons that gave us a target in the remote outskirts of the solar system. And so this is a picture, this is a discovery image from Hubble of what that object looks like. And here's what we saw with New Horizons. And so having that up close view and flying right past the object gave us this exquisite detail that you could only get with a flyby mission. We've learned some incredible things about how our solar system forms from these observations. In fact, we've been able to rule out models for how the solar system formed because of these data. And so that's related to the chemistry of this object, the way that these two lobes came together, the lack of cratering on the object, all sorts of different analysis that the team has now published to understand our earliest days of our solar system's formation. This is essentially a fossil of the early solar system because it's 4.5 billion miles away, hasn't really interacted with a lot of objects, hasn't received a lot of solar insolation. And so it's an incredible discovery, and we've published a number of papers on this discovery. So whereas New Horizons was a mission that APL built to fly to the outskirts of the solar system, our most recent launch for civil space programs is Parker Solar Probe. And that's a mission where we did the exact opposite. We built a spacecraft and hurled it towards the center of our solar system to answer questions about the sun that have persisted for more than 50 years. And to answer these questions, the science community realized that we need a spacecraft that could fly very close to the sun, literally through the atmosphere of the sun. And that simply hasn't been possible for the last half decade and more because of a lack of technologies and a lack of engineering creativity in how you do that. So APL developed those innovations. This starts with a huge thermal protection system, a heat shield essentially. It's 8 feet wide and it sits on the front of Parker Solar Probe and it protects the spacecraft. This thermal shield can reach temperatures of 2,500 degrees and it basically creates a shadow behind it. And so all of the electronics and the instruments of Parker are in the shadow and they stay at room temperature. And so you're protecting something here at 2,500 degrees and keeping all of the other components at room temperature. That's what allows Parker to go so close to the sun and study it in detail. We have a thermal management system on the solar panels for Parker, where we actually cool the solar panels by pumping water through small microchannels in the solar panels to keep those solar panels functioning. We have some state-of-the-art instrumentation on Parker, and then our mission design team came up with really a mission-enabling orbit. If it wasn't for the orbit that this team came up with, we wouldn't actually be able to fly so close to the sun. And so let me show you an example of what that looks like. This is a bird's eye view of our solar system. When I play this movie, you're going to see the planet circling around the sun. And as soon as I see it, you're going to see Parker drop off from Earth, and Parker is going to start zipping around the sun. So here we go. There might be a little bit of a lag when you see it. There goes Parker, and that's its first closest approach to the sun. It comes back out to almost Earth's orbit, and it goes back in. So roughly every 4 months, this is what Parker does. It circles around the Earth, and it goes back in. And then once in a while, it comes up and it does a little flyby by Venus. Right there, you saw one. And every time it does one of these flybys, we're essentially giving a little bit of energy from Parker, there's another one, to Venus. And we slow down the spacecraft temporarily, and then the spacecraft comes in and it comes a little bit closer to the sun. So we're able to change its orbit. And then when it slingshots back out, it slingshots back out at a higher speed. So in the first couple of orbits that we had for Parker Solar Probe following its launch in 2018, in August 2018, it came within 15 million miles of the sun's surface, which is incredible because, you know, we're normally looking at the sun and studying it from a distance of 93 million miles. That's the distance of Earth from the sun. But through these Venus flybys, we were able to drop the orbit of Parker to be first at 11.5 million miles. And then more recently, this summer, in fact, we're going to drop the orbit to be about 8 million miles. And eventually, in the next couple of years, we're going to drop Parker into 3.8 million miles from the sun. Keep in mind, the sun's about 500,000 miles across, so flying 3.8 million miles from it is really, really incredible. So this has been really a game-changing mission that has already transformed our understanding of the sun. This is a cover of a Nature issue from 6 months ago, where we published some of the first science results on Parker Solar Probe. We've learned new things about how the solar wind emerges. We've learned new things about the rotation of the solar corona. And we also have some new insights on why the corona of the sun is hotter than the surface of the sun. And so there are lots of press releases on these topics. I encourage you to take a look. Parker has already been a shining success and an example of the kind of innovation that APL brings to space science. We're very excited about it, and it has a long journey ahead of it as well. We're also building a mission to follow up on Parker. This is NASA's next major heliophysics mission. It's being developed by APL and Princeton University. It's called IMAP, the Interstellar Mapping and Acceleration Probe. This is a very exciting mission that's going to allow us to, it's a mission that's packed with different kinds of science instruments. There are about 10 instruments on IMAP, and that allows us to study different particles over essentially every energy range and put together a holistic and consistent science experiment and answer questions about the origin of the solar wind and how that wind propagates through the solar system. But then also, for the first time, build a high resolution map of the outskirts of our solar system, the outer heliosphere, well beyond where New Horizons is right now. That's a very important region of space where, you know, because of the composition and the magnetic field of the solar wind compared to the galactic wind and the galactic cosmic rays, there's a boundary region in the outskirts of our solar system, and that boundary region, we call it the heliosphere, protects our solar system. It protects life on Earth from galactic cosmic rays. IMAP is going to be the first mission to build a high resolution map of that region. So we're really excited about IMAP as our next big heliophysics mission following Parker Solar Probe. Normally at this time, I would say a few words about DART, but we have a couple of our experts from the DART team that are going to do that. So I'm just going to skip over DART and not take away from their thunder. One of the big focus areas in our civil space program right now is related to ocean worlds. You know, if you look at a picture of Earth, one of its most distinctive characteristics is, of course, its ocean. And for a long time, we thought that the Earth was unique in this respect, in the sense that it had an ocean. It turns out that's not the case. It turns out there are many places in the solar system where there are oceans, including many of the moons of the outer gas giants and ice giants. One of the big differences appears to be that they are subsurface oceans instead of surface oceans, but they also do interact with the surface. So if you see that, the picture in the middle there, Saturn's moon, Enceladus, that's a very small moon. The Cassini mission actually caught evidence of those the ocean venting into space through, you know, fissures on the surface, and so it's very exciting because, you know, one of the things that we know is where we see water, we also see life. And so this is an animation from a documentary called Aliens of the Deep that was developed by James Cameron, and this is an animation of what it would look like if you were to travel to the bottom of the ocean floor on Earth. And at this point, this is still an animation, but in a couple of seconds here, it's going to convert into a real video of what it looks like on the bottom of the ocean floor. And one of the things that you see is these geysers, these hydrothermal vents that are spewing heat into the bottom of the ocean floor. And you see life there, right? You can see life in these incredible environments where there's intense pressure. There's no sunlight, and it's very hot because of all of these gases, and yet life still thrives. And so this has rejuvenated and motivated a new search for life in our own solar system, in some of these ocean worlds, because the conditions there might not be that different from the conditions at the bottom of the ocean floor here on Earth where we see life. And so this has been a real motivating factor, and in terms of budgets and opportunities at NASA, it's become a real priority to go and look for life in these environments. So APL, working together with JPL, is building a mission called Europa Clipper, which is one of the biggest missions. It's a flagship mission to explore habitability on Europa. This is a very exciting science theme. Europa has twice the volume of water as ocean. That water is in contact with a mantle. We believe there are internal heat sources within that ocean from magnetism and hydrothermal vents. And at the same time, we have evidence that, similar to Enceladus, that water may be spewing into space. We have new observations from the Hubble Space Telescope that shows us evidence of these plumes. And so this is a wonderful location to do a systematic experiment and explore habitability on Europa. One of the things that APL is contributing to the mission is an incredible camera. It's actually two cameras in one, a narrow angle camera and a wide angle camera, that's going to capture beautiful high resolution pictures of the surface of Europa. This is a picture from a spacecraft called Galileo many years ago that shows the surface of Europa. These are the highest resolution images that we have of Europa's surface, and we only have them on over a small fraction of the surface. Europa Clipper, with the instrument that we're building called the Europa Imaging System, is going to capture images with this kind of clarity. This is in the Antarctic, and this is the kind of image that we're going to have globally across the surface of another moon in our solar system. And so this is going to be just really, really incredible for putting all of the science results on Europa into context. Another really exciting ocean world is Titan. Titan is the largest moon of Saturn. It's an ocean world that has a global subsurface ocean, but it also has another solvent. Titan is very cold, it's 94 Kelvin. And so it turns out that Titan has lakes and seas and even rainfall from liquid methane. So methane exists in a liquid state on Titan. It has a high surface pressure. It has a very low surface gravity, about 1/7 of Earth's gravity, but it has a very dense atmosphere. It has a thick atmosphere. So if you kind of combine those two factors, a low surface gravity and a dense atmosphere, that's the perfect place where you have a lot of air to move around, and it's a perfect place to fly. So Titan is a moon that has all of the ingredients for life. It has energy from sunlight, photochemistry, liquid water, methane. It also has abundant complex organics. This is a good chart that shows that. So you can see the total carbon abundance on the right-hand side of each of these places where we've taken in situ measurements. And so the scale on the right of each world that you see on this plot shows the total amount of carbon. So for example, Saturn has a lot of carbon. If you look at the scale on the left, it shows the most complex carbon-bearing molecule that exists on these worlds. And so with Saturn, for example, the carbon is not really doing anything. Titan is the only place that we know in the solar system that comes anywhere remotely close to Earth where you have these complex carbon-bearing molecules, these complex chains. And so it's an exciting destination to explore. And so we proposed and were selected last year to build a mission called Dragonfly, which for the first time would allow us to leverage this thick atmosphere and actually fly on another moon in our solar system. And so Dragonfly is going to deploy from its parachute. We're going to go direct to flight, and it's going to find a safe place to land autonomously, and it's going to sit down. Once it sits down, it's packed with science instruments. We have multiple cameras with different vantage points. We have seismometers on the legs. We have a weather station in there. We have a drill. We can sample into the Titan dirt and analyze the soil. And then once we're done with a given location, after say a month or so of science experiments, we can pick up and we can fly to the next destination. And our science team, working with our engineering team, will decide what that's going to be. And so Dragonfly will have a multi-year journey on Titan. It'll traverse hundreds of kilometers on the moon and take the next step in the search for life and understanding what we believe is the prebiotic study the prebiotic chemistry on Titan, which tells us something about the way Earth was, many years ago. We're also pushing forward with some new missions. This is a moon that I think many of you will recognize. It's a moon from Star Wars. It's a place called Mustafar. And so this was the moon where Darth Vader had his temple. It's a moon that was the part of a very famous scene in episode 3 where Obi-Wan Kenobi and Anakin Skywalker had a very exciting lightsaber duel. So it's one of the, you know, it's a scene straight out of science fiction, right? And it's a beautiful representation of an exotic world. Well, guess what? It turns out our solar system has one of these. It's called Io. Io is one of the moons of Jupiter. It's a moon that is about the same size as our moon around Earth. And Io's distance from Jupiter is about the same distance as our moon's distance from Earth. The difference is that Jupiter is hundreds of times more massive than our Earth. And so Io is just being crushed. It's being crushed at its core by the tidal forces of Jupiter because it's so close to it. And so it's, in terms of tidal heating, it's by far the place in the solar system that has the most amount of tidal heating. And in fact, I talked about New Horizons. When New Horizons flew past the Jupiter system, it took some images of Io and captured 3 volcanoes erupting during its just quick flyby of the Io system. This is a picture of one of those volcanoes. And so APL was just selected to develop a mission proposal called the Io Volcano Observer, which would be a planetary discovery mission. It would be a large NASA mission where for the first time we would go and study this moon in detail. And by understanding those tidal heating functions, we would not only learn about Io and its magma and its volcanism, but also learn a lot about the Jupiter system and how that tidal heating impacts all of the moons in the Jupiter system and Jupiter as well. So we submitted what we call a step 1 proposal in partnership with the University of Arizona that was selected, and we're going through a final down select right now. And we hope this mission gets selected and is one of the next big NASA missions to follow. So I'm going to actually stop with that. I had a couple more slides, but I think this is a good point for me to stop. But we have a very exciting civil space program at APL. We're in the core right now of a lot of development activities, a lot of new instruments and new missions. And at the same time, we're pushing forward with bold new ideas to explore our solar system and beyond. So again, congratulations to all of you, and thank you for being a part of this event. And I'm happy to take any questions that you might have.
Just so you know, you can type questions in the Q&A bar, or you can type them in as you think of them, and then we can answer them all at the end, either way.
Margaret, do you see any questions?
I see one. It says, how did you get into this field?
Oh, how did I get into the field? So that's a great question. Yeah. So I grew up in this really small town in British Columbia. It was kind of in the middle of nowhere. It's a small logging community, a few thousand people. But one of the advantages was we had really nice dark skies. And so it was great. You know, I was inspired by the night sky as a kid. I wanted to know what was out there. I was very curious. It always stayed with me. That curiosity, I remember as a kid, I had tons of space posters and space games and things all over my house. And so it's always been with me. And then it wasn't until I got into high school that I started appreciating physics and solving problems. And then when I went to university, it was just a natural fit for me to go into a physics degree with kind of it was a dual honors program that they had in physics and astronomy. And I started learning more and more about astronomy and seeing how I can apply physics to space. So that's how I got into it. And, you know, space science is such a rich field. There's so many questions out there to answer that it just kind of sucks you in, right? You make progress, you learn things, you make discoveries, you write research papers, and then it just, you get more and more motivated to do more of the same because the universe is that complicated and there are that many questions out there. And you know, this whole time, like the NASA space science program has just gone through the roof. It just continues to steadily increase, and more missions, more and more opportunities. So it's been kind of a perfect confluence of events for me.
And then this is a good one. How long does it take for a mission to go from concept to launch?
How long does it take for a mission to go from concept to launch? So it varies a little bit. So for the biggest science programs that we have at NASA, so if you look at the Hubble Space Telescope, you know, Lyman Spitzer wrote a paper in the 1940s motivating a large space telescope. And the paper was called an extraterrestrial space observatory. You know, we launched Hubble in 1990, right? So it took many decades. In terms of actual development, if you look at some of the biggest projects right now, like the James Webb Space Telescope, it's 20 years, right? From the time that the mission was prioritized to the time that we're developing the mission and planning to launch it, it's about 20 years. More typically for the kinds of programs that APL is building, you know, it can take anywhere between 5 and 10 years. You know, Parker Solar Probe is a little bit on the longer end. Some of our other planetary missions are closer to 5, 6, maybe 7 years.
And then what are some of the resources you would recommend to provide material to learn more about space and space exploration?
Yeah, so there's lots of resources. So nowadays, right, there's tons of good information online that you can use to you know, to teach yourself about space and learn about space. There's also, you know, as you get more and more advanced, one of the really cool things about space science research is that as you make progress in space science research and the science community and the space community publishes their research, those publications are available to everybody. They're wide open, they're publicly available. And so you can read about what the latest discoveries are. So if you're, you know, browsing CNN or browsing space.com and you see a discovery, usually within the press release, there will be a link at the bottom to follow up and see the actual paper that made the discovery. And that's always a fun read. It's very technical, but I think you would still enjoy it. The other thing is, you know, to look out for, you know, there's lots of public events, public speaking events where astronomers and planetary scientists and engineers that help develop NASA space program are, you know, volunteer their time and speak to the public. And so try and take advantage of some of those opportunities that might be in your communities as well. A lot of the big institutions, the universities have open, you know, colloquia and presentations and things like that are virtual these days that you can tune into. And then finally, if you really want to get involved, all of the data that's collected by NASA missions is publicly available. This is one of the wonderful things that NASA does is NASA will invest billions of dollars behind these missions, and then they'll take the data and they'll make it available to everybody. So you can actually go to different servers and you can download that data yourselves. Nowadays, there's huge projects called citizen science projects out there where members of the public analyze that data and make scientific discoveries as well. So there's really a wealth of information out there for getting involved in space, either from learning about it, from talking to somebody, from doing internships and partnerships, being involved in programs like this, like all of you are, to directly reading papers and analyzing data. It's a whole spectrum of opportunities out there.
And we're running a little low on time, but there's some great questions in here. And I'm just going to leave you hanging with this one, which is, what is your favorite space mission that APL has worked on and why?
Can I say anything other than DART today?
I think that's the answer. That's the answer. That's the answer.
Right. I'll go with DART.
But yeah, there's some other questions here. And if we get the chance at the end, we'll answer them all at the end, or we can type some answers in here. Thank you. And now we're going to hand it over to Lena, who's going to tell you all about DART.
Right, can you guys hear me? Let me know if you can hear me. Maybe type something in the chat.
I can hear you, Lena.
All right, thank you. My name is Lena Adams. I'm the mission system engineer for the DART mission. And let's see, my background is that I always liked space. In high school, I went to a space camp and then to a summer school where we did a lot of astronomy. And since then, I've just been doing a version of space physics or planetary science. And then after that, I decided to become an engineer. So I worked on the missions to Titan, Cassini-Huygens mission, that was part of my PhD, and then a Juno mission that went to Jupiter, and on an instrument that actually studied the atmosphere composition of Jupiter. Since then, I came to APL and worked in a variety of missions, including missions to Van Allen belts, the Earth belt radiation belts, and solar probe that Jason just mentioned, and Europa Clipper, which was really fun in the formulation phase, as well as the previous versions of the IRE proposal. So since then, I've really enjoyed stepping in and working on the DART mission, and which is the one that I'm going to talk to you about today. And let me bring my slides up, share them, and all right, can you all see the slides? I'm going to slide. All right, can you guys see the slides?
Yes, we can.
Somebody can. Okay, good. All right, so let's get started. So Earth Strikes Back, the NASA's double asteroid redirection test. So we'll start simply with Earth. So the neighborhood of Earth looks really dark and lonely, right? If you take any of the pictures of the Earth from space, even the ones that Jason showed earlier, it all looks very dark, like there's nothing out there. Not completely true. There are many objects in our solar system that are coming from the origins of the solar system, and they all are located in orbit around the sun, and some of them even cross the orbit with Earth. They're called near-Earth objects, and most of them are asteroids. There are some comets that also have a periodicity that they actually come close to Earth. But the point is that there's a lot of debris in Earth's neighborhood. And some of these comets and asteroids can actually come into the Earth's atmosphere. For example, in 2013, there was an incident in Chelyabinsk, Russia, where a small asteroid came into the Earth's atmosphere and it exploded. Those kind of things can happen over and over again. And when it came in, it released a giant shock wave that was about 20 to 30 times the Hiroshima bomb in World War II. So this was a big deal. You understand that it put a lot of people in the hospital and shattered windows from across many places. So we don't want these kind of things to happen all the time. However, do they? And the answer is, yeah, there's a lot of asteroid hits or small debris that actually goes into the Earth's atmosphere. We don't see a lot of it because it burns up in the atmosphere, but some of them actually make it all the way down onto the ground and create craters. So, for example, this incident in 2013 happens probably every few decades. In 1908, there was a Tunguska asteroid that came in, and that one created a much larger explosion, about 5 megatons of TNT worth of explosion. And those kind of events happen every few decades. And then, of course, you know, there's a reason why the dinosaurs are not here with us anymore. That was the Chicxulub-sized dinosaur killer asteroid that came in about 65 million years ago, and that was about 10 to 15 kilometers in size. So the Tunguska size, the 60 to 190 kilometer one, is the one that we're worried about for DART, because for the larger asteroids, we actually spent a lot of time characterizing all of the different near-Earth objects. And so we think we have covered a lot of those, and we have detected a lot of the ones that are 1 kilometer and greater. So we know where those are. It's the asteroids that are smaller than that that we're in the process of tracking. So NASA in 2016 created this Planetary Defense Office. So please understand that NASA has been doing this for quite some time. It's just that they didn't have a special office that's specifically dedicated for planetary defense. So the Planetary Defense Office has quite a big charter. It is supposed to search, detect, and track the asteroids and small objects around Earth and chart them to know what their orbits are. So if they come close to Earth, they're able to tell that it's going to intersect Earth. They also need to characterize what these asteroids are made out of. Are they a rubble pile? Are they a solid chunk of metal? Or are they a solid chunk of rock? That makes a big difference to what happens as that rock is coming into the atmosphere. Will it burn up If it's icy, it most likely, of course, will disappear in the atmosphere. If it's not icy and it's a rock, it might actually make it all the way to the surface, depending how much heating there is. So that's what part of the Planetary Defense Office does, is that they need to be able to characterize all of these different asteroids. And they do that via both ground-based and space-based observation. They plan and coordinate between all the different agencies, also all around the world, because this is not just a US problem. This is a global issue that people have to deal with and learn how to deal with. So they coordinate with other agencies, and they also mitigate. And we are the first mission, DART is the first mission that actually mitigates the threat of an asteroid. So as you can see in this column right here is DART. And also, of course, then they assess how this threat was mitigated. Okay. So this is basically DART in a nutshell. There's a big moon, there's a little moon, we are hitting the little moon, and that is basically it. We're going to demonstrate the asteroid deflection with the kinetic impactor, which means we hit the little moon and see how much it changes the orbit of the little moon. So let me tell you a little bit about DART. So we're launching in 2021, and you can see our spacecraft. We're going to impact Didymos B, which is a moon of a larger asteroid called Didymos A, in 2022. The spacecraft is also carrying a small CubeSat called LiCiCube. And that CubeSat is going to fly by the smaller moon right after we hit, and is going to image the crater and the ejecta. Ejecta is all the stuff that's going to be picked up once we actually hit the moon afterwards, and then send pictures to Earth. So we're targeting this binary system and going to impact Didymos B to change its orbital period, and then we measure the period change from Earth. At the time of the impact, Didymos system, so both of these asteroids, are going to be at their closest approach to Earth. So we are actually able to watch the impact from the ground telescopes and see how much the period of the Didymos B around Didymos A is going to change. So Didymos is really an ideal target. So if you wanted to go and you wanted to hit an asteroid, what things do you need to worry about? Well, number one, you need to worry that by you hitting an asteroid, it didn't put it on a trajectory that it would then try to impact Earth, right? So that's number one. Safety is very important. And by going to a binary system, we're able to see how much change we would actually impact. But the Didymos B is still going to stay locked in the orbit around Didymos A. And so then it's a very safe experiment to make sure to see how much do we actually change the orbit, and it will actually make it really good. So let's see. So the orbit that we're trying to change, Didymos B orbits Didymos A at a period of about 11.92 hours. And if everything goes well, we can change the orbit by about 10 minutes. So we'll be able to watch it from the ground and see that Didymos B orbit has changed around Didymos A by about 10 minutes. So how big are these asteroids that we're trying to hit? So Didymos A is about somewhere between Burj Khalifa and One World Trade Center, so about 780 meters in diameter. And our Didymos B is about the same size as the Statue of Liberty. So it's very small, 163 meters. This is the first time humanity is actually going out to hit an asteroid that is that small. And that's a very hard thing to do. And Michelle is going to talk a lot about that. And that's what SmartNAS is all about. Our size of our spacecraft is about a school bus size. So we are fairly small, but we're going really fast. And that is one of the keys here, is that you go fast and you impart a lot of momentum into Didymos B. So in addition to just being impactor on the asteroid, we're demonstrating a lot of other technology for NASA. So we have in order to be able to hit Didymos B, we have this autonomous smart navigation system, and that's what this talk is really about. And that means that we autonomously seek out the moon that we're trying to impact. And then we fire thrusters and do maneuvers in order to make sure that the spacecraft is actually impacting the moon. And we do all of that autonomously. We are using the Draco imager, which is basically our camera, our telescope, to detect the moon from far away, about 30 days out. And then we're using it as the optical measurement in order to be able to point ourselves and guide ourselves into the moon. We are also demonstrating the NEXT ion propulsion engine for NASA, which is a development that has been in the works for close to 16 years at NASA. And it allows us really great things. In the future, this kind of engine could be used to change your trajectory in space in a very simple manner and not have to bring as much propellant with you. And that really helps us because for space, the hardest part is really getting off the ground. And once you're off the ground, it's really hard to bring a lot of mass into space. And this NEXT ion engine helps us with that. We also, another exciting technology that we're demonstrating are the rollout solar arrays. The typical solar arrays that you see on the spacecraft are rigid panel, which means they are very, very stiff. These are basically blankets that are on this special roll, and they roll out and snap like a snap bracelet. And these are the type of solar arrays that we're demonstrating on this mission as well. So a little bit about our friends, the Light Italian CubeSat for imaging asteroids, LICIACube. So it's a CubeSat that we're bringing along with DART that is provided to us by the Italian Space Agency. And it's based already on the CubeSat that is going to be flying on the Artemis mission to the moon. And it has a couple of cameras, and the plan for it right now is that we release it about 10 days out before we hit the asteroid. And then it follows us in, images the plume, takes pictures of the crater, and hopefully sends them back. So because once we hit the asteroid, there's really nothing left. There's no way we can transmit the images back. So a little bit about our spacecraft, just to give you a sense of where we are. So here's the spacecraft itself. It's about 2 meters by 2 meters. So basically 6 feet by 6 feet. And this spacecraft has the LICIACube on the side, you can see it right here, and has our imager, Draco, with the cover on one side, and the engine that I just talked about on the other side. It also has the solar arrays that are rolled up on the sides of the spacecraft. And when they roll out, the spacecraft becomes about 18 meters long. So understanding this really tells you what are some of the challenges that we have to deal with as well. The whole spacecraft is also controlled by hydrogen thrusters. We have no reaction wheels, so we have to fire thrusters anytime we want to maneuver the spacecraft or change its attitude to point at the moon, to point at Earth, or anything like that. So the other thing is that on the corner right here, you will see the high gain antenna, which is our way of communicating and sending the video back to Earth as we're about to hit the moon. So now I'll talk a little bit about the DART challenges. So look at the spacecraft, beautiful. However, it does have really long solar arrays. It has the Draco, the camera right here, and it has a high gain antenna on the other side. And here's the LICIACube right here. So what are some of our challenges? I mean, one of the most challenging things is that we really know very little about the object that we're trying to hit. So Didymos has been observed a few times, the latest in 2003 when it was the closest approach of Didymos system to Earth. The only object that we are able to see during that time, of course, is the main moon, which is 780 meters in diameter. On the left, you can see the little Didymos actually passing through based on the ground observations, just you can see Didymos is just passing through, and that is all you see from the ground, right? And that's all we know right now. There are some preliminary shape models based on some radar observations. So in 2003, when the Didymos A came close to Earth, they bounced off some radar off the surface, and they came up that that's the shape of Didymos A. However, we really don't know what Didymos B looks like at all. The only reason we even know that Didymos B exists and that there is a moon around Didymos A is that when we watch it, doing light curve observations, we are basically plotting the brightness, how bright Didymos A is. We see it dipping at certain times, which means that there is a moon or something passing in front of Didymos B, and that's how we Didymos A, I'm sorry, and that's how we know that there is a small moon orbiting this larger moon, and we're trying to hit that moon that we have never seen. So a bit challenging, and we actually won't know what it looks like in time to hit it. This is kind of the timeline of what's going to happen as we get closer to the moon. So at 30 days is the first time when our camera is going to be able to see the Didymos system, which means it's going to see the main asteroid, Didymos A. And we're going to be watching it. We're going to be doing updates to our trajectory based on where that moon is and trying to get us as close as possible positioned in order for the autonomous part to take over. So 10 days out, we're going to start having continuous ground coverage, and which means that we're talking through the Deep Space Network and through the antennas on the European side called ES-Track. The tracking service. Basically, we're communicating all the time, and we're able to troubleshoot and make sure that everything is ready for our terminal phase. So at 8 hours out, we begin preparing our spacecraft to go into the autonomous mode. And at 4 hours out, we are in a most crucial part of the whole mission. It's called the terminal phase, which means that the ground has given all the control to the spacecraft. The spacecraft is completely autonomous, and the SmartNav guidance is enabled. And at that point, we just let the spacecraft completely take over. The spacecraft has a variety of things to do. It has to be able to point at the moon, find a main moon, then find Didymos B, then point the high-gain antenna to Earth and stream pictures the whole time while it's trying to hit Didymos A, and also point solar arrays at the sun. In the meantime, all of the processing has to be done in order to be able to do all of this autonomously. So it's a fun challenge. So at 60 minutes out, so 1 hour out, this is the first time we're able to see Didymos B. And we're finally starting to target the right moon. And as we go in at 4 minutes out, it is only 21 pixels in our camera. So tiny little moon at 4 minutes out, and we're pretty much done maneuvering, and we can't really change very much at that point. So then at 2 minutes out, Didymos A drifts out of the field of view of the camera, and then hopefully in 20 seconds out, we are finally at the resolution that our investigation team wants in order to be able to pinpoint where are we impacted. Because where you impact on Didymos B is actually super critical, because you don't want to impact on the corner of Didymos B and just send it glancing below. You want to impact right in the center to give it as much push as you can. And then at that point, we hit, and hopefully we all go home. But the problem is also that we only sort of know where Didymos B is right now. So you can see there's a picture of Didymos A and Didymos B, and we're trying to hit Didymos B. The most important thing is that we're using an optical camera, right? So we're doing all of this visually. So if the moon is in front or behind Didymos A, we won't be able to see it, and we won't be able to hit it. So it is very important for us to get our timing just right when then the moon is as far away as possible from the separation is as big as possible from the main asteroid. So it's kind of like trying to thread a needle. And you have to do it while imaging and sending data back every second. So you are going at 7 kilometers per second, which is close to 15,000 miles per hour, really fast. And you're streaming images back real time, including in the last 7 seconds, we have a requirement that we have to send data back in the last 7 seconds. And that's very hard to do. And we're very happy to say that it's looking really good for us that we can do that. It's a very big challenge because you're doing a lot of processing in your avionics in order to be able to get that far, and also continue firing thrusters and adjusting the spacecraft as needed in order to be able to stay pointed at the moon. So how do we know that this actually works? Because we don't really know what the moon looks like. So here are some of, basically what we do is we do tons of simulations on the ground and with hardware in the loop. We vary the moon a lot, right? We vary how the moon looks like, whether it is a sphere or a weird misshapen dog bones case. And that's actually a very challenging case because if you're watching that case, you are seeing 2 blobs come together, and when your algorithm is trying to distinguish which one is actually the moon and you're trying to go for the center of the moon, where are you going? To that blob or the other blob? So they're challenging cases that we simulate. And we run lots of simulation, high fidelity test beds on both hardware and emulations of the spacecraft. And at this point, I'm happy to say that we're now starting to run this on the spacecraft itself. So looking really good. And we have to hit every single time. We have a requirement that we have to be within 15-meter distance. And this is just one of the simulations that shows that we have to make sure that we hit every single time. And that is a requirement before we launch. So next, we also have to not run out of fuel at the end. A lot of the missions, you know, they use fuel for their scientific observations throughout the mission. In our case, we have to save up that fuel all for the end in order to be able to hit. So, we're doing a lot of maneuvering right up till the end. And we have only 50 kilos of hydrogen that we're bringing with us. And that hydrogen has to last us the whole time in order to be able to hit. So very important. The other thing, of course, we have to image the asteroid, and because it's not going to happen after impact. We have to point this camera at Didymos, and it's a really great camera. It has a really high resolution. It can see something of its, size of a chair from Baltimore. If I was in DC, the camera was in Baltimore, we'll definitely be able to see a 1 meter thing. So it is a really good camera, but pointing that camera is very tough because of the solar rays that we're demonstrating as well. They're great. They're very light mass, amazing arrays, but they're also incredibly floppy. And apparently trying to maintain your pointing with something that is extremely floppy, very hard, very hard. So I'm not going to show all of this movie because I'm going to save this one for Michelle, who's coming up next, who is actually going to talk about SmartNav. But this shows you how we actually simulate some of the SmartNav, and that's coming up next. So just one last word about the solar rays. I just wanted to show you kind of the scale of what we're talking about here. So are we going to practice once we're in flight and try to figure out, because this is something you can't really practice on Earth, right? We don't have an asteroid that we can simulate. We have lots of simulations, but we don't actually have an asteroid to go and hit, right? You'll have to test as you fly, and how do you do that? We're planning to practice on the moons of Jupiter, actually. After we launch, we're going to point our camera at the Jupiter system, and we're going to spend some time looking at the moons coming out from behind Jupiter, in particular Callisto. And that's how we're actually going to train our SmartNav algorithm. And also we're going to do a lot of image processing, guidance and navigation, and then send the data back to Earth real time in order to be able to characterize how our solar rays behave in flight, because that's really hard to do on Earth in actual gravity environment. So just want to finish up by saying that I really love my job. We get to really work with an amazing team of very dedicated and talented people, some of which are pictured here, including folks from SpaceX, from APL, and many other institutions. We also get to explore. You know, we're going to find out a lot about the formation of the solar system by studying some of these objects, and asteroids are some of the earliest objects in our solar system. You know, the remnants of when the solar system was actually forming. And of course, we're going to save humanity and crash a $250 million spacecraft into an asteroid, and that's called success. So with that, I think I'm going to end right here. And if you guys have any questions, I'll take them now.
There are a couple in the chat, and this is my favorite. Based on this, it sounds like they started way too late in Armageddon, which isn't really a question. But.
Sorry, Margaret, can you repeat the question? I couldn't hear you.
Based on this, it sounds like they started way too late in the movie Armageddon.
Yeah, I mean, it would be nice if Bruce Willis would join us for these talks, but this is this is a different mission. We are not sending humans into space, and in fact, it's better not to send humans into space when you can do it all robotically.
All right, and some of these questions are great, but we're running a tiny bit short on time, so maybe we'll go on to Michelle, and then we'll come back to some of these questions because we can type some answers in the chat.
Okay, sounds good.
Okay, so I am Michelle Chen. I have been at APL for decades now, and I came right out of school, and I have had the privilege of working on so many different projects. So one from developing a DEXA scanner that allows us to measure bone density of the astronauts before and after they've been in flight. I also worked on the prosthetics program where I was the software and controls lead, and I am currently the Smart Nav lead. We like to say Smart Nav because small body maneuvering autonomous real-time navigation is a mouthful. Hang on, there we go. So Lena started out with why she loves her job and ended, and so I'm gonna start with why I love my job. I get to work with just an amazing group of folks. A couple of them are actually not pictured here, and just creative and really smart people. And I wanted to highlight our degrees because of the fact that all of us have actually, with the exception of two, and one of them is working on their master's, but we all have our master's. And then we have 4 that actually went and got their PhDs. So this is in these different fields, and I kind of wanted to share them with you. It's something that, you know, we all kind of love learning, and we're always learning. Oops. All right, so the other thing, I'm trying to minimize some of these windows because they're getting in my way. Okay, so the stuff that you're learning in school, actually we apply it to the Smart Nav algorithm. So there's physics, there's geometry, there's algebra, there's linear algebra. All of these things is the basis of the Smart Nav algorithm. All right, so I wanted to do a baseball analogy. One of the reasons is because I like baseball and I kind of miss not being able to watch it right now. And I do want to note that I am not a Red Sox fan, but this is just a fantastic catch. And the analogy is that SmartNav pretty much does exactly what an outfielder would be doing if playing baseball. So at the beginning, you know, we're looking at the batter, looking for the baseball to come off the bat. And once it gets hit, we're kind of make a guess at what that velocity and trajectory looks like. Then you start running, and you have to correct your ground trajectory. Sometimes the ball will get lost in the clouds, sometimes in the lights. And so that is like a perfect example of what happens with SmartNav. So we roughly know where to look, and we do get that initial guess from the navigation team. We are definitely booking at, Lena said about 7 kilometers per second. And just to let you know what that is, it would get us from Baltimore to Chicago, driving on the roads. We could get there in 2.8 minutes. And we are still 16 times slower than the Parker Solar Probe spacecraft, top speed to date. Lena also mentioned that we fire the thrusters to do our trajectory adjustments. And then the GNC team has such a hard job, because what they have to do is they have to keep the Dynamo system in our field of view. And one of our guys came up, I didn't double check his math, but he basically said it's like looking through 6.5 soda straws. And we do this once every 2 seconds. So just to give you an idea of what that is, this is at the geometry at 5 minutes from impact. So the Dynamo system is here in our field of view if we were perfectly pointed. But if we were just 1 degree off, this is where the Dynamo system would be relative to where we are pointing. And it is a hard problem. So SmartNav. We start out with getting the images from Draco. And the first part of the algorithm is we do detection and blobbing. And what I have here as an example is I made it easy so that it's just spheres to get the point across. But the detection algorithm is essentially looking for something that's higher intensity than the background. And then we have this technical term called blobbing, and it really is a thing, so you're welcome to Google it. And what that does is it takes all the pixels above the threshold value and puts them together and identifies them as a blob. So once we have the blobs identified, we do a centroiding scheme, which essentially finds the center of these blobs. And as Lena pointed out at the beginning, we are just kind of aiming towards the Dynamo system because we can't see the two. And then as we progress, the secondary does separate from the primary, and the targeting algorithm has to differentiate between Didymos B and Didymos A. The guidance filter, what it does is essentially what the baseball player would be doing as far as guessing where the ball will be so that the baseball player gets there at the same time to catch the ball. And so we're predicting, we have the measurements all the time, we're predicting where the asteroid will be when the spacecraft is supposed to hit it. The maneuver logic, we could not stick with the baseball analogy. I mean, we could have, but the car one was a little easier. And it's basically it's sort of taking into account how much fuel we have left, how much propellant we have left, and then doing the maneuvers at the most optimal times. So you saw this graph from Lena, and what you see here is that, this at 4 hours out, you can't. This is what you see, and Didymos is there. It sometimes looks like dust on a monitor. And I won't go through this again, but it's 60 minutes out. This is what you see. Now this, just to give you an idea of this range. So the range here at 4 minutes to go, this range is the distance from Baltimore to Jackson, Mississippi. So it's always interesting to see how this all works. And then at the coasting for the final 2 minutes, that's the distance from Indianapolis to Camden Yards. And so at that point, we stop maneuvering because, as Lena pointed out, these solar panels, while awesome, make the GNC work much harder. And so we're not thrusting, we're not causing any perturbations to the spacecraft at that point so that we could get images for the investigation team. So this video is essentially showing, this is at 30 times speed up. This is an indication of the thrusters that are firing as we maneuver. This is the example of the attitude control that needs to be in place to keep the Didymos system in our field of view. And it's, you know, if you look at it too long, you could actually get motion sickness, or some of us do. So some of the algorithm here, what you'll see is this terminology zero effort miss is describing what would happen if we just went off of the navigation inputs. So at the very beginning, the nav team gives us an estimate of where they think the Didymos system is. And so we aim towards that. And if we did absolutely no thrusting, this is where we would end up if we don't employ SmartNav. And then what you saw was a transition. So the aim point went from Didymos A to Didymos B, and that's a result of the targeting algorithm. These things that we're identifying as tracks, these are what we kind of keep as part of the targeting algorithm. And what we're doing right now is, so you could see some of the drifting that's occurring. So we're not thrusting. You see the maneuver logic happening. I'm just going to let it play out a little bit. Part of the reason that we also don't joystick this is that it would be impossible to do this because we have a 72-second light time delay. So once we get the images, if we were to joystick it, 72 seconds for that information to get to the ground, we would have to do something about it, send it back, another 72 seconds. And that type of reaction time would just be too slow for the speed at which we're traveling. Okay. And lastly, I kind of wanted to show the different schools that we all went to on the SmartNav team. And that is all I have.
Righty, and we have a few questions left over, and we will answer them. And we have, if you have any other questions for any of our presenters, we're happy to answer them. So feel free to type in anything relevant to what you've heard this afternoon. Michelle, does this algorithm use any machine learning?
It does not. So we actually do not need that complexity for what we're doing here.
And then this one is interesting. How does it maximize the kinetic energy it hits the asteroid with?
I don't know if Lena wants to field that. So for me, momentum transfer is, you know, is mass times velocity.
Exactly. And so, you know, many missions that I have worked on, you know, the hardest thing to, as I said in my talk, the hardest thing to bring into orbit is mass, right? Because that means that your launch vehicle has to lift all of that mass out of Earth's gravity, and that's incredibly hard. So this is the first mission where we actually are not wanting the spacecraft to be very light because of that, right? We want it to be pretty heavy, and we want to be going fast. So our trajectory allows us to go fast at close to, you know, 7 kilometers per second. And we are about 600 kilos. So you can do the math and see what kind of momentum we're going to impart into the asteroid. Of course, you have to make some assumptions about what the asteroid is made out of, right? Is it pure rock? Is it an ice? Most likely we're thinking it's actually our carbonatic chondrite asteroid, so which means it's a lot of rock. And basically that will tell you how much momentum you'll transfer and how far you will move it.
And there's also the hope. Yeah, there's also the hope of the ejecta is going to.
Exactly. That's right. So when we hit it, it's going to create ejecta, which is basically a plume of stuff coming back. And that is going to actually accelerate the asteroid further. thus decreasing the orbit. That's helping us if we hit from the side of the asteroid, that will actually allow us to decrease the orbit. We're still deciding whether we're going to increase the orbit or decrease the orbit, and it's based on many different things. Okay, I was kind of answering more than a question.
All right, and then what programming language is used to coordinate this task?
So we, oh, do you want to answer that?
No, you go for it.
So we actually employ quite a few different languages. We start out the render and camera emulator that emulates the asteroid system that you saw on the videos. That is actually done in C++. The original SmartNav guidance filter and maneuver logic was all implemented in C++. And then we moved it over to MATLAB so that the GNC team typically does everything using Simulink. And Simulink then, there's a tool that auto-generates that code into C. And what actually gets deployed in the flight software is C. And then part of the SmartNav algorithm is actually implemented in VHDL, so FPGA code. So a lot.
Yeah.
There we go. And then the one last one. Have you thought about using aerospike engines?
I don't even know where they are, so I'm abstaining on this one.
Neither do I.
So the answer is no.
All right, and I think that's it for the questions. If there's any more, we can tune in and answer them again. Amber, did you have any final remarks?
No, not to add to this wonderful presentation, but I did want to thank you all very much for this fabulous insight into DART and how the engineering and the programming behind it. And I wanted to wish all the teams good luck this weekend as they are going into the judging phase of this competition. So best of luck to you all. And I'll see you at the awards ceremony. That's Sunday at 7 o'clock. It's next time we're all online. So that's it.
And the questions were great. I just really wanted to point that out. I love the questions.
Yeah.
And I double checked, and it looks like the rendering will be done on Monday. So we'll post the link to this presentation on Monday. But you're going to be busy working on the competition this weekend anyway, so it's probably just as well. Jason, did you have any final remarks?
No, just thank you all for coming and good luck, and thank you also to Elena and Michelle for some great presentations. I learned a lot about DART, so that was really exciting. Thank you.
All right,
Bye,
and have a wonderful weekend, everyone. Thank you.
Bye.
Thanks, Margaret.
Bye.